Thank you very much, Wing, for having invited me to give this presentation on the chemical and isotopic constraints on the origin of the moon. And along with me in this research are Sébastien Charmeuse, Frédéric Monnier, and Romain Tartez. And we'll give you a bit of an overview to start with. I'm not sure how much you've already heard about where the lunar samples come from, but here is a map showing the approximate locations of the Apollo landing sites. And what you'd notice is that they are all from the near side of the moon and from an area around the Procolarum Basin, sampling both these darker regions, which are known as the Lunar Maria, and these lighter regions, which are known as the Lunar Highlands. So indeed, then most of our information about the constitution of the moon comes from these samples. So these are the Maria, these are the Highlands. And the Maria basalts are called Maria because they are from the Latin sea, and they are the low-lying areas, several kilometers lower than the Highlands. And they can be, the rocks from these Maria are broadly basaltic and can be classified according to their titanium content, so the titanium content of the whole rock. And these range from the very low titanium basalts with less than about 1.5% titanium oxide, low titanium between 1.5 and 6%, and then high titanium, which are more than 6% titanium oxide in them. They're also generally relatively high in iron and therefore have a low Mg number compared to terrestrial basalts. There are also some secondary criteria which we're not too worried about here. The other, as I mentioned, the other suite of rocks are known as the Highlands suite, and they are also quite distinct in their character chemically because they form this bimodal magmatism in which we have the Faroan anorthosite or fan suite, and these have high anorthite content in plagioclase, so very calcium rich, and their Mg number, that is their magnesium to magnesium plus iron ratio, is essentially constant, even if the magnesium number decreases at constant anorthite content in these fans. On the other hand, we have the Mg suite, which extends to higher Mg numbers, but also shows a broad positive correlation between the anorthite content and the Mg number, which is indicative of magmatic differentiation. So this is a sample from the Mg suite, which is a troctolite, so olivine in green and plagioclase in white, 76535, which is known as the most beautiful sample to have been taken from the moon. The third component, it's not really a rock type, is known as creep, so potassium, rare earth element, and phosphorus. And this is defined by its trace element composition, and it's sort of added as a spritz to the other lithologies that are present in the Highlands suite. And so we don't actually have samples of creep per se, but we know that it exists from its trace element signatures observed in other samples. So just to give a bit of an overview of the chronology of this magmatism, we can see that the Mare basalts are generally younger than the Highland suite, and this is also attested to by the fact that the surface of the moon on these areas is far less cratered than it is for the Highland suite. And so the Highland suite is largely composed of the Faroan anorthosites in terms of volume, with lesser amounts of Mg suite and subordinate amounts of other lithologies such as the creep and/or alkali suite compositions. So this is sort of an overview of how we understand the composition of the moon through the analysis of these lithologies. So taking a step towards a broader picture of how the moon formed, one of the prevailing theories was that of the giant impact, and still remains that of the giant impact. And this sort of really gained ground in the 1980s when it was recognized as a natural progression of planetary formation. This is because as the planet grows, there's gravitational focusing effect, which leads to the relatively faster growth of larger bodies at the expense of smaller ones, which is so-called oligarchic growth. Now, in the canonical model, the idea was simply to try and reproduce the high angular momentum observed today of the Earth-Moon system. And to do so, models settled upon this figure of about 15% of the mass of the Earth as an impactor, which then impacted the proto-Earth. I guess Mattia spoke a bit about this earlier, but just to suffice to say that in this canonical model, it predicts that the Moon is largely made from the material that was initially present in the impactor. So then the question became, is this actually observed in lunar rocks? So the answer is probably not. When we look at the chemical similarities when we look at the chemical composition of lunar and terrestrial basalts, we see that they are indeed quite similar, especially when considering the variety of compositions observed in other planetary materials. So here's a ceochondrite, here's the eukaryote parent body, which has been identified as Vesta, and this is the Shogar-type parent body, otherwise known as Mars. And what we see is, in particular with these elements, manganese, chromium, and vanadium, that the Earth and Moon have extremely similar patterns of depletion, which are not observed in any other bodies. And this is special because we think that, for example, manganese can only be depleted to this extent. So this is the abundance relative to Ci chondrites. So the abundance of manganese can only be depleted to such an extent by core formation, which occurs at extremely high pressures. And Earth is the only body that's big enough for this to occur. And the fact that we see the same depletion on the Moon means that because the Moon was too small to form its core at such high pressures, that this chemical signature was inherited from the Earth. And this led to the idea that the Moon was predominantly inherited from the Earth's mantle, which had been proposed even before the Apollo missions. So the idea is then that this result is actually quite at odds with the canonical model, in which the Moon was formed predominantly from the impactor. However, there's not just chemical evidence that the Earth and Moon are similar, but there's also isotopic evidence. So here, this is a famous plot by Paul Warren, in which he shows the mass-independent isotopic variation. Now, mass-independent means that any variations that we see are due to small differences in the nucleosynthetic abundances, i.e. the abundances of these isotopes that were formed in star-forming processes, and have then been inherited in different zones of the protoplanetary disk. And so depending on perhaps the heliocentric distance of the body, we see differences in isotopic compositions. And this is well delineated by the carbonaceous chondrites, which plot in one group, and the non-carbonaceous chondrites, which plot in another group. And this is for titanium and chromium, but also for oxygen, as well as chromium here. But the really important point to take here is that the Earth and Moon, regardless of which system we're looking at, always plot together. So this is also very strong evidence to suggest that the Moon and the Earth were formed from essentially identical planetary building blocks. If we look at mass-dependent isotopic fractionations in this case, and this is isotopic fractionation that is engendered by separation of phases. So for example, during core formation, we have preferential isotopic enrichment in the core relative to the mantle, or during volatility related processes in the gas relative to the liquid. And again, here we see that as a function of the element's volatility, if we're looking at relatively refractory elements, we see that all of these isotopic systems are again identical. So this plots the isotopic difference between the Moon and the Earth, and they all plot essentially at zero, i.e. no isotopic difference. This argues for a derivation of the Moon from the Earth's mantle. However, if we're now moving away from the refractory elements and we move towards more volatile elements, we see that this concordance that we observed on the isotopic and elemental abundances of these elements breaks down as the elements become more and more volatile. So this, again, is the normalized abundance relative to the sun or relative to CI chondrites. And we see that the Earth's mantle in green has a higher quantity of these volatile elements than does the moon's mantle in gray. And so there is a process that has preferentially affected the abundances of these elements in the moon relative to the Earth. And it is this process that we would like to know a bit more about, and because it may have important information as to the conditions at which the moon formed. So in order to say something a little bit more about this volatile loss, we can use isotopes to try and quantify the conditions under which this occurred. Now, isotopic fractionation during volatile loss can take two n-member forms. The one n-member is the kinetic isotopic fractionation case, in which the fractionation factor of two isotopes I and J of element M between the liquid and the gas depend essentially on the inverse square root of the masses of the gases that evaporate. And so this is easily predictable. It's independent of temperature and only depends on the mass of the gas species that is evaporated. Importantly, because the light isotope always moves faster than the heavy isotope, this means that the residual planet, or in this case the moon, always becomes enriched in the heavy isotopes. The other n-member is if isotopic fractionation were to occur at equilibrium. And again, this is also predictable, but in this case, it depends not only on the isotopic mass, but also on the temperature squared, as well as the relative bond strength between the liquid and the gas phase. And so depending on whether this term here in brackets is positive or negative, we can produce a heavy or light isotopic signature in the moon. And so we can try and estimate whether kinetic or equilibrium conditions occurred on the moon by looking at the isotopic difference between the composition of the moon and the Earth here. So what this shows is the isotopic difference plotted as a function of how much of the element is lost. So the F refers to the fraction of the element that remains in the moon relative to the Earth's mantle, i.e. its initial composition. And the higher this value, the more volatile the element is. So if we look at elements like lithium, magnesium, silicon, they are plotted at 0, 0. That is, they are not lost from the moon and therefore do not show any isotopic fractionation. But as we follow this trend towards higher ln F, we see that the most volatile element, zinc here, is actually also the most fractionated. And this has some significance. The slope of this line has a significance in that it can be related to the saturation factor of the gas at the surface. So when S is equal to 1, the kinetic term goes to 0 and we're at equilibrium. That is S meaning the pressure at the surface relative to the equilibrium partial pressure. However, if S is 0, then essentially kinetic effects dominate, and we have the kinetic end number as I showed before. What we see is that the fractionation is much, much smaller than we would expect for a kinetic process. Indeed, we can quantify using this trend that the value of S would be about 0.99. So that is essentially 99% of the equilibrium value. And so this, these data provide very strong evidence to suggest that whatever process caused the volatile depletion on the moon, this process was essentially at equilibrium between the vapor phase and the melt phase of the moon, which we think occurred after some sort of lunar magma ocean. However, I mentioned that in an equilibrium regime, we could either expect to see heavy or light values. And so in order to test this idea, we measured a couple of years ago chromium isotopes in terrestrial rocks, so peridotites and komatiites that should be representative of Earth's mantle, as well as lunar mare basalts and MG suite rocks. And what we observe is that although there is a spread, we can see that on the whole, the MG suite and the lunar mare basalts are lighter than Earth's mantle, which is shown in blue here. And so this difference actually is quite in contrast to what we see from the other isotopic systems in which the moon is always heavier, as we can see here. So how do we rationalize the fact that the moon is actually lighter in chromium isotopes than it is in the Earth? So this comes down to the difference in the way in which chromium evaporates from magmatic rocks. So on the left, we have the reaction which could cause chromium to become lighter in the moon. And this is a reaction in which chromium 2+ in the melt plus oxygen goes to chromium 4+ in the gas. And if we look at the isotopic composition, so this plots essentially how heavy or light the phase is, we see that chromium in the gas would expect it to be heavier than chromium in the melt. Whereas the opposite is true for these other systems which are actually heavy in the moon. So potassium and zinc both have gas species which are more reduced than the species in the melt, and therefore the melt is actually heavier than the gas. And so we can see that at equilibrium, we indeed expect chromium to be light in the melt and these other elements to be heavier in the melt. And again, this is the fact that we see that chromium isotopes are indeed light in the moon is another indicator that volatile loss occurred at equilibrium conditions. So then the question becomes, how physically did this come about? How did it actually lose its volatiles? So to answer this question, this goes back to a study that Sébastien Charnoz presented perhaps a month earlier, and I'll just give you a brief overview of how this links in with the observations. So to start with, we wanted to explore a process that had not been explored before, actually. The current models for the way in which you may deplete the moon in volatiles is either can fall into two categories. The first being viscous spreading, in which as the protolunar disk cools, the disk spreads out and we have a separation from vapor, which stays connected in the interior, and vapor depleted solid material, which is spreading further out beyond the Roche limit, which I'll explain in a little bit. The other newer theory for the formation of the moon comes from this synestia model, which is essentially a large supercritical donut in which we have, perhaps in the outer reaches, condensation of this supercritical fluid and or gas into small droplets, and it is during this process at equilibrium, maybe at about 2500 Kelvin, that we could enrich this phase in the liquid phase in refractory elements, and the gases stay partially in the gas phase, which is then accreted back into the Earth as the synestia contracts. However, there's a couple of unknowns with these models. Firstly, if we want to lose volatiles from this system, then we need extremely high temperatures because the gravity of the Earth and Moon together is quite substantial. Secondly, the physics of these disks are still very poorly known, making quantitative predictions quite difficult. Thirdly, we don't know that how much of this material, for example here, is actually ejected already beyond the Roche limit during the impact phase. And if this is the case, then there's no scope for volatile loss to occur before the material is ejected. So here we want to investigate another mechanism, which is actually we show to be quite a constant process that occurs for all satellites forming in the vicinity of a larger body. Just a bit of background to help quantify how easily atmospheres can be lost from planets or planetary bodies such as the Moon. The escape parameter, which is shown here, is quite a useful indicator of how this can occur. So what this plots is essentially the ratio of the escape velocity, which scales proportionally with the size of the body or its gravitational pull, and the thermal velocity of the gas, which of course scales with temperature. So the larger this value, then the larger the body or the smaller the temperature, and therefore the harder it is for the atmosphere to escape from that body. If this value is small, then temperature can be high and atmospheric escape is quite easy. So if this parameter is larger than 1, we have this scenario in which Jeans escape occurs. And this is the formula that calculates the mass loss rate. So change in mass as a function of change in time, as a function of this escape parameter. And what we can see is that if we have a proto-lunar atmosphere, which is at about 2000 Kelvin and has a molar mass equivalent to that of sodium, we see that the escape velocity of the moon, which is 2.38 kilometers per second, is rather large with respect to the velocity of the gas particles. So this is a cumulative velocity distribution of a Maxwell-Boltzmann gas. So the kinetic energies follow the Maxwell-Boltzmann distribution. And we see that only about 5% of the gas molecules have velocities that are sufficient to be able to escape from the moon. So in this scenario, we have a very inefficient mode of volatile escape from the moon. However, this is when we consider that we need to accelerate a particle to infinity away from the lunar surface. However, if the moon is forming at the Earth's Roche limit, this is no longer the case. So as I mentioned, the Roche limit can be defined as the limit at which the gravitational disruption of material is no longer strong enough such that we can have coalescence of small bodies. And so for the Earth-Moon system, this occurs at about 2.5 to 3 Earth radii. So a distance of about 15,000 kilometers, we can start forming the initial fragments of the moon. So what is the importance of this Roche limit in terms of atmospheric escape? Well, what we see here is that here is the escape velocity of the moon, 2.38 kilometers per second, if we need to accelerate a particle out to infinity. However, if we only need to accelerate a particle to a distance such that it then becomes trapped by the Earth's gravity, then the energy required is significantly lower. So what we can see here is that if the moon is forming at 3 Earth radii, then the velocity that you need for a particle to escape is almost half of that of the standard escape velocity. And so what this means is that atmospheric escape is highly favored when we have a small body forming in the vicinity of a larger body because of this effect. So this is the effect of Earth tides. So in this case, we no longer have this Jeans escape regime. We decrease this V escape parameter, and we now have an escape velocity which is much lower from the moon. And this at the same temperature, so we can see that the curve here of the gas velocities is the same. We've just simply changed the escape velocity of the moon, and this pushes us into the hydrodynamic escape regime. This is where the atmosphere becomes hydrostatically unstable and is subject to a gross outflow of material from its surface. And this occurs when more than 50% of the gas particles have velocities greater than the escape velocity. And so this is the scenario that we are dealing with in this treatment. Just a quick detail as to how the gas actually escapes. We perform numerical simulations to show the position of the gas molecules as they're escaping from the moon. And what we see is that gas escape is favored from the moon here at the L1 and L2 Lagrange points, which are the points of the lowest gravitational potential energy around the moon. And so the Earth in this frame would be here. And so we have these low potential points which facilitate the escape at these regions. And so this dynamical simulation illustrates that it is indeed possible for escape to occur from this Hill sphere. Okay. So the way in which we model this is to solve the Parker-Wind equations, which were initially developed for loss of the solar photosphere. And we do this scaled to the moon in the presence of the Earth at different Earth-Moon radii. So this includes equations for mass conservation, the conservation of linear momentum, and conservation of energy. And with these equations, it's just suffice to say that we can self-consistently solve for the pressure temperature structure of the atmosphere around the proto-moon. And now we go into a little bit more detail about how vapor surrounding the moon is lost. So these are the results of the model. We can show here that what we're plotting is the escaping flux of material in lunar masses per year as a function of the surface temperature of our lunar atmosphere at a fixed Earth-Moon distance of 2.5 Earth radii, i.e. at the Roche limit. And what we see is that the total escape flux, of course, scales with temperature. So at low temperatures, we have relatively low loss rates, 10 to the minus 8 lunar masses per year. And if we're at 2,500 Kelvin, we can lose substantial amounts of lunar material, about 10 to the minus 3 lunar masses per year. Of course, this picture then changes so the colors represent different amounts of condensates. So if we consider that as the atmosphere escapes, some of the atmosphere starts to condense, that provides then additional energy in the form of the latent heat of condensation to fuel further escape. But this is essentially a free parameter in the model. So then what we have, if we move the moon further away from the Earth, the escape flux decreases. And this is due to the effect that I mentioned earlier, in the sense that if the moon is closer, then the Earth's tides are more powerful, and we can subtract or attract more of the lunar atmosphere that escapes. And so this is the general property. So as the moon moves further away, the amount of atmospheric escape decreases. And this then provides two mechanisms to arrest lunar atmospheric escape. The first being by simply cooling the lunar surface. So we initially start at perhaps 2,500 Kelvin, and as we cool down, the escaping flux decreases. And the second is if we stay at a constant temperature almost, for example, and we simply move the moon away from the Earth, as it has been doing for since its formation. It's now 384,000 kilometers away. This is another mechanism that causes a decrease in the escaping flux. So how do these link then to the conditions at which volatile depletion occurred, and can these conditions be reconciled with chemical and isotopic data that we observe in lunar basalts and lunar rocks? So this is a useful plot to consider when we're thinking about how planetary materials lost volatiles. So the standard reference for planetary materials is shown in these CI chondrites, which essentially have solar-like composition. And here we plot the manganese-magnesium ratio, which are two elements that behave in a rather similar manner, except for the fact that manganese is more volatile than magnesium. So for these are the chondritic meteorites. And what we see is that even though the manganese-magnesium ratio decreases, so we go from volatile rich to very volatile poor, the manganese to sodium ratio, which are both volatile elements or moderately volatile, strictly, this ratio is essentially unchanged if we look at the chondritic meteorites. However, when we look at small planetary bodies, including the moon, we see that these bodies all have manganese to sodium ratios which are much higher than manganese to sodium ratios in chondritic meteorites. And this can be reconciled with the way in which these two elements evaporate. So manganese is present as 2+ in the melt, and sodium is present as 1+, and they're both present as monatomic gases. this means that they have different dependence on the oxygen fugacity, i.e. how oxidized the body is, in which if the body is more oxidized, then manganese becomes less volatile than sodium. And so the fact that these have elevated manganese-sodium ratios indicates that whatever caused the volatile depletion in these bodies was quite distinct from the reduced conditions in the solar nebula. And this can be indicated as well by thermodynamic models, in which we show here that the role of oxygen fugacity is quite important, in the sense that we have, under nebular conditions, an oxygen fugacity shown in bar here of the nebular gas, which is controlled by the hydrogen to water ratio of the gas and is actually relatively low. However, when we look at evaporation from planetary bodies, we see that their oxygen fugacity is essentially controlled by the evaporation of SiO2, or into SiO plus O2. And they are several orders of magnitude more oxidized than in the solar nebular gas under which the chondrites formed. And so this indicates that indeed high FO2s are expected during volatile loss that occurs on planetary bodies as opposed to the solar nebula, and therefore they cannot be considered a simple inverse scenario of nebular condensation. And so in order to predict how elements are lost during volatile depletion phases on planetary bodies, we need to consider the appropriate reactions, and therefore not nebular condensation temperatures, which have often been used for this purpose. In order to do so, we can write a generalized reaction in which we have our proto-moon here, and we can consider an element M with an oxidation state of X plus N, bound to some amount of oxygen in the liquid, and that evaporates into a gas species with an oxidation state of X, again bearing the same metal, plus N on 4 moles of oxygen. And depending on the stoichiometry of the reaction, we can write this for a series of elements and define their partial pressures like so. So we have to assume some sort of initial concentration, which is given here by the mole fraction. We have an equilibrium constant for this reaction. We need to set the oxygen fugacity, which, as I mentioned, is to be relatively oxidized. We have the activity coefficient here, which describes the way in which this element dissolves in the silicate melt. So how this element dissolves here. And of course, for the gas phase, the partial pressure can be considered the same as the fugacity, because we consider it to be an ideal gas due to the relatively low pressures. So in order to characterize what these, how high the pressure evolved is during these reactions, we had to experimentally determine these properties, i.e. the equilibrium constant and the activity coefficient, experimentally for each of the metal species that we're interested in. And so this was done a couple of years ago as well. Once we have the partial pressures of the individual elements, we can sum these up to give us the total pressure of the atmosphere, which is then fed into the dynamic model, which describes the atmospheric structure as a function of height. Because if we know the pressure at the surface, we can then calculate what the pressure will be at the Bondi radius or the exabase, which are the points of escape for hydrodynamic escape and for Jeans escape, respectively. So if we look at the thermodynamic model using our experimental data for the lunar atmosphere, we can see some interesting trends. So, of course, the higher the temperature that we assume for the lunar surface, the higher the gas pressure evolved for each element. So this is the pressure shown here on the y-axis and temperature on the x-axis. And what we see is also that sodium is the most abundant element in the lunar atmosphere, the protolunar atmosphere, followed then closely by zinc in green and potassium in orange. And these are all relatively minor elements in the liquid, but actually the dominant species in the gas. And even though magnesium, iron, and silicon are the most abundant elements in the liquid, they're actually far less abundant in the gas, simply because they're not as volatile as these elements here. So with this sort of information in hand, we can try and predict how much of each element is lost, and in relative terms as well. So in fact, we can do this by comparing the relative depletion of such volatile elements with respect to one another in lunar rocks, and comparing that with our experimentally determined thermodynamic model. So what we really only consider are lithophile elements, i.e. those that are present in the silicate mantle of the protomoon, because we don't want to bias our results by considering the depletion of elements that may have occurred during core formation. So in order to get an idea for the relative depletion of two elements, so for example, I've shown here zinc plus an alkali, so zinc oxide in the liquid plus an alkali in the gas equals zinc in the gas plus alkali oxide in the liquid, in this case plus 1/4 O2. So we can use these sorts of reactions in order to quantify the conditions under which they occur, because they are sensitive to, as you can see, the oxygen fugacity, but also the equilibrium constant of this reaction. So half R to the left, half R to the right is this reaction as a function of temperature. So we can constrain both the FO2 and the temperature. And what we do is perform a Monte Carlo simulation 1,000 times, in which we vary slightly the equilibrium constant of this reaction within its uncertainties. And then we predict, based on this, the depletion of the other element in the moon. So we reference all of our depletions relative to zinc, because its abundance is relatively well known in the moon, and it's also a lithophile element, which can be used appropriately as a reference, and is fixed at 0.052. So then based on differences in equilibrium constants, we can solve, given a certain amount of depletion of zinc, how much the other element, E, will be depleted. And again, I show here that this depends on the equilibrium constant of this other element, as well as the oxygen fugacity under which this depletion occurs. So here we substitute E for all these other elements here, not zinc, but that's included as the reference element. So we can write a series of equations based on this generalized equation, in which we have E equals magnesium, gallium, lithium, sodium, potassium, copper, and rubidium. And we solve all of these equations simultaneously in order to obtain a minimum misfit to the observed abundances in the moon. And so this is what it looks like. So in our Monte Carlo simulations, we can see that by randomly varying the temperature and the oxygen fugacity, we observe the best fit to the abundances as shown here. So the points in red are the actual abundances of these elements in the moon, and the points in grayscale are the results of the simulations, the best fit of each simulation, which is given by as a function of the 1,000 points that were modeled. And so what we see is that, in fact, the abundances of these elements can be reproduced relatively well for a wide variety of the simulations, except for gallium, which may be partially in the lunar core. And so by doing this, we can then look at the temperature and the FO2 at each of these points that reproduced our relative abundances, and see what conditions then result. And so this can be seen here, which is a contour plot showing the misfit to the model as a function of the temperature and as a function of the oxygen fugacity under which the evaporation occurs. So this point here in this blue zone indicates the minimum value, the minimum difference between the model and the data. So this is something that's just come out in a paper by Romain in PNAS just a couple of weeks ago, or last week. And what it shows is that the observations are best reproduced when the temperature is at 1650, plus or minus about 130 Kelvin, and the oxygen fugacity is 2 log units above the phalite magnetite quartz buffer. And this has a relatively larger uncertainty, as you can see here. And so using the relative abundances of these elements in the moon, together with thermodynamic data, we can actually best quantify what the conditions were under which the moon lost its volatiles. So if we consider the total amount, so we've been able to explain the relative depletion of the elements, but now if we consider how much in total of these elements needed to have been lost, we fall upon a value of about 0.1% of a lunar mass must have been lost to decrease their abundances to the observed values. So if we then compare this constraint with the models that we showed earlier for lunar loss rates, if atmospheric loss were to have occurred at the Roche limit, essentially, then we see that we have lunar loss rates of about 10 to the minus 6 lunar masses per year, whereas at 5 Earth radii, we have slightly lower loss rates of maybe 10 to the minus 7 lunar masses per year. So if atmospheric loss was to have occurred around this distance, then losing 0.1% of a lunar mass requires about 1,000 years if the temperature was at about 1650, as indicated by the abundances of the moderately volatile elements. And indeed, these 1,000-year timescales are actually quite similar to those that we would expect for magma ocean cooling timescales. So the magma ocean crystallizes and loses heat over time, and this process is relatively short-lived. Just a final note now, looking at isotopic fractionation. As I mentioned before in one of the earlier slides, we showed that the saturation factor, so this pressure on the lunar surface relative to the equilibrium pressure, is greater than 0.99 based on the isotopic compositions of lunar rocks. Now, in the classical Hertz-Knudsen theory, we see that a Maxwell-Boltzmann distribution of velocities is centered on 0. So we have half of the particles that return to the liquid, and the other half do not. And so this leads to a net velocity of 0. However, if we have our hydrodynamic escape scenario, then we no longer have a net velocity of 0. Actually, we have a net positive velocity away from the lunar surface. And so the gas is non-stationary. And as a result, our Maxwell-Boltzmann distribution is no longer centered on the 0 value, but it's displaced to a higher value. And therefore, we have fewer particles that return to the liquid. And the net result of this is that the partial pressure at the surface relative to the equilibrium pressure decreases to values below 1. So we need to find circumstances in which this upward velocity reproduces values that are still greater than 0.99. And we can do this by the following equation here, which shows that the partial pressure, or this factor here, the P surface on the P saturation, is equal to some function of the thermal velocity of the gas and the surface advective velocity of the atmosphere. This can be then plotted in a, as shown here, in which we plot this surface velocity versus the thermal velocity of the gas against the Earth-Moon distance as a function of different temperatures. So this is the highest temperature curve, which shows that you can actually reach relatively low values of this factor. So we can reach values that are about 40%, or about 0.5 if we have a very hot protomoon very close to the Earth. However, these high values are inconsistent with the isotopic constraints that we showed earlier. So the isotopic constraint shows that this value has to be less than 0.01, i.e. 1 minus 0.99. So it can only be the values that satisfy the observations for the moon can only be within this zone here. And again, considering our constraints from elemental abundances, we see that about 1600 Kelvin, the Earth-Moon distance would have had to have been about 3.7 Earth radii for evaporative loss to have occurred. And so these are the sort of the tight constraints that we can place on the position of the moon and its ensuing volatile loss based on its chemical and isotopic composition. So these are the conclusions. We have a physical description of a phenomenon that occurs for all celestial bodies, for example, binary stars and close-in exoplanets. It obviates the difficulty of losing an atmosphere from a high mass Earth-Moon disk because we have the presence of the Earth, which propels this escape. We see that the timescales over which this atmospheric loss occurred probably about 10 to the 3 years. We show that the conditions under which volatile loss occurred were relatively low temperatures, about 1650 Kelvin, and high oxygen fugacities, and that atmospheric loss must have occurred at equilibrium in order to satisfy isotopic constraints. So thank you very much. I'm not sure how I went for time. I hope that was okay.
Yeah, you're doing very well. Thank you for this. I would say it's geochemical talk, very different from what we have heard before, and so we have to refresh our chemistry, which I had forgotten 50 years ago. There are any questions, from the audience, and I hope there are some experts interested in this talk. I have a couple of questions though. That is because from your calculation, you set a very stringent, I would say, constraint on the mass loss rate and time scale. Such as you say, for this to happen, the moon has to be at 3.7 Earth radii, and at the time, the whole thing could only happen. Duration is about a few thousand years. But then the lunar orbital evolution, the lunar evolution process is a kind of gradual thing, right? You don't just happening at that time and then everything, then stop. So before and afterward, there must be a continuum.
Yes, I agree. I think I would say that these are average values integrated over the lifetime of the moon. So I guess, as you said, we can't just have one specific value that wouldn't be realistic physically. And so perhaps this 1650 Kelvin relates to an average value that is integrated between, I don't know, 2000 and 1200 Kelvin or something like this, depending on how long the moon spent at each of those positions. But I think the more effective way of preventing atmospheric escape is via crystallization of the magma ocean, which occurs relatively quickly, about 1,000 years. Although that's not our work, that's based on some other estimates, but it should be relatively fast. So that maybe then give you a short cutoff time.
So if it doesn't work out that way, if the crystallization time scale, is longer, then you might have to modify the model then.
Yeah, I agree. I think, maybe we're open to new constraints.
And more work, right?
Yeah, exactly.
Which is good. Now, so you think that, assuming that everything goes as well as you can tell, would this problem be solved now? That then there's no more things to be done by correcting more lunar loss. Like you say, okay, stop going to the far side to pick up samples because I am already, I have done everything.
Well, so one of the ideas that we put forward in this paper well, this is Romain's idea, that because all of these rocks come from the lunar near side, he suggests that this volatile loss could be due to the impact that caused the Procolarum basin, rather than being a global moon sort of event. And so I think it's really fundamentally important that we also look at the lunar far side and other areas so that we can get a better global distribution of the chemistry of these rocks to better inform our hypotheses.
So you should convince ESA to go to have a lunar mission to go to the far side.
Exactly. I think there is something that's just landed on the lunar far side, isn't there? Is that right?
Oh, it's Tower 4, but it's not. It's not a sample return mission.
Yeah.
Yeah.
Needs some sample return.
So you have to, okay, to test your theory, you have to work harder to convince the agencies, to have a new.
Yes, exactly.
Yeah.
I think that was kind of his intention, to sort of provoke the agencies into saying, "Oh yes, we should look at that."
That's good. Any questions from the audience? I mean, they're all saturated by your information.
Yeah.
But I think that because your video has been recorded and will be posted. So then like now, like I am using the video material for my teaching. So I see. Every night I'm watching the videos, So
no, sure, exactly.
I'm sure I come back to your video many times to make sure I understand everything.
Yeah.
And for me, the students ask questions. So usually I will write to you and write to people.
Okay. I see. It's a good way of outsourcing. Yeah.
Right. Passing the buck.
But exactly. But as you can see, this is kind of a mixture of a couple of studies, because I think one of the traps is that people don't often consider a lot of different constraints in a holistic manner. So we want to try and be consistent with both dynamics, chemistry, and isotopes, which is quite difficult to reconcile all together. And so
that's great, because it's a very good example. It's an example of interdisciplinary, research. I'm sure that Sebastian would just feeling helplessly, with this chemistry thing.
Yeah, I'm not sure how much he described of the chemistry actually in his earlier talk. I'm sure he described this sort of model. But,
no. He saw some of this thing. If you could go to his videos to see.
Yeah.
One thing he said that is that he found that there's so much zinc being lost. He felt that it's not doesn't feel right.
Yes, exactly. That problem is overcome.
Okay.
By you need the high oxygen fugacity. So if you go to low oxygen fugacity here, or high temperature, then zinc becomes way too volatile, and so you end up losing a lot of zinc and not much sodium and potassium. So we can see here that sodium and potassium are almost as depleted as zinc.
Okay. Yeah.
So if you have, if you have something in this region, for example, then the pattern would look something more like this.
So one important thing I learned from your talk is that the oxidation state is very important,
Exactly.
In this game, right?
Yeah, and that's indicated by this equation like this. So if you say that this is A instead of this could be sodium or potassium.
Yeah.
And so this tells you that you need to have a certain FO2 in order to reproduce the same ratio that you see in lunar basalts.
Because for us who solve a Parker-Wien equation, we say, oh, just Parker-Wien, everything lost, that's all. We don't realize that there's still chemistry going on,
Yeah, exactly. I mean, the Parker-Wien, you lose everything that's in the atmosphere, I guess, but depends what's in the atmosphere.
Everything is just a particles, right? There's no chemistry.
Yeah.
Okay, exactly. Paolo, thank you so much. Yeah, I mean, that's a great talk. I mean,
Thank you very much for the invitation.
Yeah.
Appreciate it.
And maybe when you have good new results, come back and tell us, right?
Yep, will do.
Okay, thank you. Have a good time.
Ciao.
Yeah. Ciao.